Hey, welcome to Statistics. This is the introduction to statistics in the new IB course, first examined in 2014. And where did that word come from anyway, statistics? What does that mean? Well, I've got a little screen clipping here from Hayes and Harris, and other screen clippings in this presentation will come from Pearson's textbook. And this guy, Sir John Sinclair, back in the 18th, 19th century, came up with this definition of statistics. I think he actually created the word to mean inquiry into the state, there it is, the key word, into the state of a country for the purpose of ascertaining the quantum of happiness enjoyed by its inhabitants and the means of future improvement. Wow. Wow, what a statement. Well, anyway, we can see that the state still remains as a key focus, if you like, on statistics, because we do try to ascertain various things about the population or the inhabitants, and I guess for the means of future improvement. I guess that's true. We collect data and analyse it, and that's what statistics is, collection of data and then analysing it to say something about the state of a situation somewhere. Well, that's good, isn't it? So I wondered if you knew that one. Anyway, statistics, there are two aspects to the word statistics. First of all, it's the area of mathematics that deals with that. That is, we're trying to collect data and analyse it and say something about it. And then it's the other one, it's the values we calculate from a data set, from a data that we have actually collected. Values we calculate are sometimes called statistics. So, in other words, come on down here. You might have done this before. Adding up all the numbers, see that there? Add up all the x's, x1, x2, etc. That may be the heights of people, and divide by how many there are, and we get something called x bar, or the mean. The symbol is x bar. And the IB love good mathematical notation, don't we all, as budding young mathematicians? And here it is, the sigma notation. It means the sum from I equals 1 to n. We've seen this in sequence and series work as well, of xi's. So that means xi could be x1, x2, right up to xn. It's a label for the particular data point that we've measured. And this sigma means we're going to sum them. The sum of, Greek letter sigma, meaning in maths a sum of, and then of course we're going to divide by n. So that's a definition of something that you've probably been doing quite a bit, like what's your average math score? Okay, in test, add them all up, divide by how many there are. I hope it's a big number. Good luck with that. Anyway, so the calculation of this mean from a sample is called a statistic. So there are two actual ways in which we can use that word statistics. In plural, it means the area of maths, and singular, a statistic is a value we calculate from a sample, which is our set of data, if you like. We're going to come and look at all these things in a minute. And here's another one, of course, another big calculation here. May not have seen this before, the sample standard deviation, trying to measure how spread the data set is. We won't look at that now. That's going to be fun for later on. But over here, I guess you would have done some of this, trying to represent data with well, it's not a sketch, is it? It's a plot. It's a histogram in actual fact. A column graph there, where you've got groups here of your data grouped up, and you're recording how many are in each group with the idea of getting an idea of what's going on, or come back up the top, the state of the situation. Statistics. Got it? Right, it's going to be fun, and lots of technology we can use here, and the new course embraces that. So let's get into it and come on down and see some definitions for a start, so we've got our language for maths. And here it is, descriptive and inferential statistics. Descriptive and inferential. Sounds like a big word, inferential, but it's exciting stuff. Descriptive statistics are concerned with collecting, summarising, describing the characteristics. I think you might have already done some of that, you know, measuring the times you take to get to school maybe, and drawing a histogram to say, hey, many times I take a lot longer than others. Just get a picture or a state of the situation. And we're only usually concerned here with the data collected. And we don't make an effort to generalise it, to say, well, this is what's always going to happen, or any inference like that. Whereas in inferential statistics, we select a random sample and try to represent the whole group of individuals or items that we're measuring in a population and make some generalisation. This is going to come later in the course. This is in the course, but it's under something called binomial probability distributions and normal probability distributions. So that's an interesting one for later, where we're making an inference and trying to say something about what? The state of the situation in general. Okay, so let's get busy and get going with this descriptive statistics part, because that's what these next few presentations are going to be about. So come on down, more language to come, more language to come. But let's just get a picture here, and a picture of what we're doing. Over on this side, what we're doing is descriptive statistics. We've collected a set of data. We're going to do that down below here in a minute. And we've drawn a histogram, and we've done a calculation of a mean. This is your times going to school. You didn't know that, but I'm telling you now here, this is the times it took you to get to school. And it ranged quite broadly there. And you can get an idea then of, sometimes you get there quite quickly. Other times, maybe this is on math test days, oops, I shouldn't say that, you take a bit longer. So you've got a picture, and also down here you've got a statistic calculated. It's called the mean. You've added up all the times, divide by how many there are, and you have an average or a mean called an X-bar. Now, I don't know whether you've seen that symbol before, but that's the symbol for the mean or the average. Okay, so that's descriptive statistics, isn't it? Over here, what's this? Okay, this is a good picture coming from Pearson's now. That's a population here. That's a large group of items. It could be people. Population does not necessarily mean people in statistics. It means a group of individuals about which you're trying to say something in general, make an inference or infer or try to summarise what's going on there. The state, remember states, this is, the state of that whole group. It could be all the motors made by a car manufacturer. What are they like? What are these? Hey, they could be high-performing ones, green ones, different, and some in there, triangle ones, trying to say there's a bit of diversity in this population. And what we're going to try and do is summarise what we feel in general is happening there. What is the inference for that total group? What are we going to do down here? Look at this arrow. We're going to grab a bunch of individuals taken at random, usually, at random, right, from the population, giving every member of the population an equal opportunity of being included in that sample. So here we are, we have a small group of them, which are pretty representative, we hope. It's got some triangles, it's got some green stars, it's got, so every individual of different types hopefully is represented, and hopefully in the same proportion as what they occur in the big population. Now, we don't know about that. There looks to be a few too many pink stars there, I think. Don't know. But random is the key word here. It gives every individual an equal opportunity of being included. Okay, but doesn't necessarily ensure that they are. So not always does a random sample give us a good sample to summarise the population with. But what we're going to do is that what we're going to talk about in this course, but we're going to imply back to that. We're going to work on this sample and look at what it's saying and then make some inference back upstairs there. Okay, now this is not part of this first section of the course now. We'll be doing that a bit later on. We're just going to be doing descriptive statistics. But I think you can get excited about this, can't you? I mean, you can see the power of this process when you're looking at maybe predicting who's going to win an election, or predicting how far your motor's going to go. when you buy this car, this new car, let's say, if you're lucky enough to buy a new car, then what is the expectation of the life of the motor? Have they sampled and they've given you a mean, an average or something? How sure can you be about yours? Yours comes from somewhere in there, mate. And will yours have the same mean as a sample mean that we have measured? All right, so interesting stuff. And remember, I think we're going to do well in determining the state of the situation with our statistics. Okay, let's keep going and have a look at a bit more language here. Okay, here we are. What are we measuring? Well, we're measuring a variable, aren't we? Something that's varying, whether it be time you get to school, or who are people going to vote for, length of lifetime of a motor in your car. So a variable is a characteristic that changes or varies, and that's what we're interested in, measuring the state of it, measuring statistics around it over time and for different objects under consideration. So this is exciting, and when we measure that measurement is called data or data, I don't know, who knows, data. Anyway, so we got that, a whole bundle of measurements. Okay, trying to measure what's going on here, what's the state of this situation. You can see I'm getting quite carried away with that origin of the word statistics, meaning state. I'll calm down in a bit anyway. So here we go. We've got some data, and what type could it be? Well, it could consist of numbers, couldn't it? Times taken to get to school, and numerical or quantitative data, so you've made some measurement of the size or the quantity. That's where quantitative comes in, the quantity value, if you like, the value of the quantity. And over here, categorical or qualitative. That's a group that you've fallen into, like who you're going to vote for. Okay, party 1, party 2, party 3, and that's qualitative. It's just the quality of the response. It's not an actual numerical measurement and quantifying it. Quantifying it means the quantity, the size of the value. Quality is the nature of the value. So here it's categorical because it's in groups or categories. Okay, it's not a number situation. Okay, so who you'll vote for, party 1, party 2, party 3, that sort of thing. Whereas over here, you are measuring times gets to school, or heights of people, and so on. And then when you've got your numbers, what sort of numbers can you have? You can have discrete numbers, separate ones. Okay, what's that an example of? Well, what's an example of that? Sorry. Well, the number of 1s, 2, 3, 4, 5, 6s you get when you roll a die, a singular for dice. You know, you could get data that way. You could get, in 20 throws, you could get 4 6s, 3 5s, etc., and list them all out. That would be discrete answers. What would be continuous data? That would be perhaps measuring heights of people, or weights of people, or times it took you to get to school. You could get more and more accurate with your measurement there, and that would be continuous data. You know, it took me 12 minutes, 4.2 seconds or something. Okay, continuous measurement. Depends on how accurately you can measure it there. But that's the idea. Different types of data are going to come out from us measuring a variable, and that's a characteristic of the group that we're looking at. Okay, let's do some more. We're almost to the exciting part. A bit more language here, but then we'll get on. Categorical or qualitative data measures a quality or characteristic of the experimental unit. These definitions now are coming from Pearson's. The categorical data yields a qualitative response. That is, it's a type rather than a quantity. So, what's the type? Well, the type is, I vote for this party, or I have brown eyes, or I have blue eyes. You're in a category or a type. You're not actually making a numerical measurement. So it's the quality of the thing. It's a qualitative response, and here's some examples. Categorizing students into first year IB or second year, into math studies, etc., or political affiliation, party 1, party 2, party 3. Have you got it? Getting the idea? Well, what about numerical or quantitative data? Quantitative variables, measuring numerical quantity or amount of each unit. Quantity data yields a numerical response. Quantitative data. So with that sort of data, like height, how can you measure that? Well, you generally would measure it in centimetres or something like that, depending on where you are in the world. And so you're getting a number. And that's a numerical or quantitative answer. Okay, so that's numerical data. Notice that was an interesting one, because height could be qualitative, couldn't it? You could say short, medium, tall, and have categories. But by and large, that would be called a quantitative variable and would yield numerical data. Numbers to measure the nature of that variable. And the variable would be height there. Okay. Examples: yearly income of company presidents, the heights of students at school, the length of time it takes students to finish their lunch or to get to school, and the total score you receive on exams are all numerical. Okay. So you're getting the idea. We're going to be playing around with different sorts of data here in descriptive statistics. Okay, come on down. And now we have the idea of, with numerical data, discrete data is where you have single discrete responses, like I toss a coin 20 times, how many heads do I get, how many tails do I get? I can't have 1.5s there. They are separate responses. Usually here, not a bad idea from Pearson's, coming from counting. Okay, so discrete data, the number of times I get a head tossing a coin 20 times, that sort of idea. Okay, I've counted up how many I have. Okay, continuous data. Well, that's the idea of measurement and the fact that you can measure between values. So somebody 150, 160, 180 centimetres tall or whatever, then you could have 180.1, 180.15, etc. So it's a measurement that is continuous. It isn't just in separate integral values or separate values at all. It has a continuum, if you like. Time it takes a student to travel from home to school. That's an example. Okay. So are you ready? Let's go and grab some data now and see what we can do with it. All right, here it is. This has come from Pearson's. This is the weekly expenses of a student in euros here. In euros. We can't do that very well. In euros. Okay, so the interesting thing here, of course, is this has been rounded to the nearest euro. So really it would be on the continuous side, wouldn't it? Although we were always round it back to a decimal of some sort in money. But here we have a set of, I think there are 80. How would you tell? How can you quickly work out how many data points there are there? Okay, want to do some maths? Okay. We've got 5 rows. And if we quickly add up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16 columns. So what have we got? Hey, it's like an area problem, isn't it? The total is equal to 5 lots of 16. Lots of means times multiplication, multiple addition, right? Do you know that? Multiplication is multiple addition. We have 5 lots of 16. That's 16 plus 16 plus 16 plus 16. See? See how multiplication is multiple addition. So 5, 16, multiplication to the rescue. Instead of doing that, we're going to do 5 16s or 80. Okay, so 80 data points there. Some little bit of interesting maths in the background hanging around there, isn't there? I think that's a reason also, you might think about this, that the area of a rectangle is length times breadth. Is that the same? I think so. Number of squares there. Think about that one. Okay, so what are you going to do? When you measure these average expenses in euros for a week of these students, look at what you've got. You've got a mass of data, and people are going to say, hey, honey, I don't understand what you've got there. Hey? All those numbers, what's it mean? Okay, so descriptive statistics to the rescue here. Let's find the state, oh, there it is again. Let's find the state of the situation, okay, by doing something with this data. So come on down, what do you reckon we do first? Are you right? What do you reckon we're going to do first? Uh-oh, were you right? Here it is. we're going to make a table to summarise the data here. That might not have been the first thing you might have thought of, but I think the next thing will be the thing that you thought of, maybe. Oh well, we'll wait and see. Alright, so what have we done? We've grouped the data. How do you do that? Okay, so grouping the data into these groups here to make some sort of a graph, then what are you going to do? Let's look at the lowest value in our data set. Our lowest value, I think, is 38. And I think the highest value is, does it get to 70? I'm not sure. I think it got to 68. I think only 68. Okay, let's say it got to 68. Now they aren't very convenient numbers, starting at 38, 68. And go to 68, sorry. What we usually do is say, let's call this about 35, a nice figure, either the 10s or 5s. We'll finish on 30, 35, 40, that sort of idea. So it's easy to read scales, you'll see that in a minute. And take this maybe to 70. And what we're trying to do is to have between 5 and 10 groups. This is the common idea, so that we can group the data and see what's going on. If you've got less than 5, you haven't got much of a breakdown. If you've got more than 10, you've got too big a situation. It's all spread out, if you like. We'll talk about the shape of those distributions in a minute. So there's the first convention. We make between 5 and 10 groups. Well, 35 to 70 is a distance of 35. Now, if we made them into, so here, 70... take 35. I'm showing you how to do this. Actually, in this course, there's a big emphasis on using technology, which is down below. We'll come and look at that. But 70 take 35 is 35. Now, if I divided by 5 groups, that would be a group size of 7. Oh, that's not usually done. In groups of 5 or 10, usually. So let's divide by 7 groups, and they would be groups of 5 units width. 5 euros width. 5 euros width. Okay, so that's what we've done over here. Come across here now. 35 but less than 40. 40 but less than 45. So this less than means you go right up to 40, so that's 39 point whatever, and that would be in that group. But once you hit 40, you're down to the next group. So I want you to get the hang of this, because even if we represent it on a histogram from the calculator, or a bar graph from the calculator, don't know whether you know much about histograms yet, we'll come to that in a minute, then you need to have this idea of how to group them. How would you actually do this? Pearson's have actually summarised it all ready for us here, but I want to go back and say, how do they get that number of students in that group? So your first step is to set up your groups. 35 less than 40, 40 less than 45. So here, this is how you do it. Highest minus lowest, taking convenient numbers. Between 5 and 10 groups, getting a convenient width. You'll see why we do this when we go to read off our histogram once we've actually constructed it. Okay, so how do you record data? You go to the first data point, 38. You put a line through it, and you put which group it's in. Then 50. Go to 50 is this one. It's not in this one. It's less than 50. It's just in this one here. Then 55 is in that one. 60 is in that one. So you have what's been left out here is a tally column. Tally them up. And then when you're finished, well, let's say, what have we got here? In this group we've got 11, so as we go through we get to that. Every fourth one, the other one you lay down across it, so you can easily see bundles of 5. Do you get the idea? Every one you get, the next, after 4, next one you lie down. So that would give you 11 there. That's a convenient way. You only scan the data, scan once, which is, of course, as we move on with technology, that's the way you would record this anyway. It would be scanning. But let's say you were doing it by hand. You read each data point once only and record it in a particular group in a tally way, and then tally them up here. Remembering every bundle of 5, the last one is laid down so you can easily see how many bundles of 5 there are. You don't want to come up here in 21 and be counting 21 individual strokes. Too hard. So every bundle of 5, that last one lay down. Okay, so you've got that. And what about this now? Percentage of students. Percentage of students in each group. How do you do that? Well, just revise percentage over here. It's the number divided by the total times 100. So let's check the first entry. 2 out of 80 times 100 equals 2.5%. Correct. Okay, so you can actually convert all of this column to percentages. That might be useful. Okay, let's go down and see what the histogram might look like now. And this might have been what you would want to do first. I don't know. Did you suggest perhaps drawing a graph? Because most people would not like that table we drew. That would still be too hard for the average person. So here it is. A histogram's graph consists of vertical bars constructed on a horizontal line. Oh yeah, too many words there. For the variable. So here it is down here. This is the variable, and this was the weekly expenses. And that's what we would generally put under here, and in the unit, euros. Okay, and generally we don't put the midpoint. We would put and there should be a little bit of a gap there, 35 to 40, 45, 50, like that. We would generally put our scale there conventionally. Now, we will use the midpoints later on, and with technology that's quite often the case. It displays midpoints in a different way. We'll have a look at that later. Here we've got frequency. Sometimes, because you might be measuring different numbers of people in different situations, you can have the percentage here. Okay, the percentage frequency there. So that gives you an idea if you're trying to compare another group and you haven't taken as many, the columns won't be as tall. But if you change it back to a percentage, you can compare between graphs. Okay, so that's not a bad little trick as well, to use percentage there. All right, well, what sort of shapes do you get when you draw sort of histograms like this? And I want to try and summarise that now and say, have we got words to describe these different shapes? So just come down here a bit. We'll put this one in the middle, this one here. This is almost symmetrical, isn't it? That's a bit high here, and we haven't got this end on the other side there. But that's pretty symmetrical. So we'd call that virtually a symmetric or symmetrical distribution. Now, sometimes you don't get patterns like that. You might get more something like this. No, I don't want to put too much up there. Let's put it more like this. And this is called a uniform distribution. Not much happening. It's sort of uniform across everything. Very hard to say much about a distribution of data points like that. You could have a bimodal distribution. Bimodal suggests you've got sort of peaking in two different areas. Bi, as usual, meaning two, bicycle, bimodal. Two modes, two common values. I don't know whether you've had that yet. A mode in a distribution is a most frequent score. And there's two scores there. Two modes. Okay, bimodal. What's this? Well, this is a symmetrical or symmetric distribution. Symmetrical. One mode there in the centre. Unimodal, if you like. And then, of course, what if you disturb this a bit? Let's say we have, well, this is a bit like it up here, isn't it? Can you see what we could have is this and maybe too many chunky bits on the high end. So it's sort of got some symmetry. Oh, and this messes it up. So this is called skewness. because the symmetry is skewed high. Let's put all the different ways people talk about this. This is skewed, most mathematically I suppose, skewed positively. So it's pushing up to the positive side, to the right here. Skewed high, because they are the higher values, or skewed to the right. There are actually 3 different ways of describing that distribution. And so what do you do? Let's do it again, and let's skew it differently. So we might have something like this. Okay, maybe just lower this one a bit less obvious. Can you see that basically we've got a nice symmetrical distribution there? This is in the way. This is actually skewing it, skewed off. It doesn't stay in the middle like it should be, if you like, whatever way you like to think of that. So this is skewed what? Down the negative end, negatively, or low, or to the left. Okay, so they are the ways we describe histograms and distributions. And the idea is to see, is there symmetry? Yeah, this one's not bad, not bad. If there isn't, like, what's disturbing it? What's the bit that's a problem? And up here, what would you say? This would be skewed positively, wouldn't it? Now, skewed positively. Because if we looked at this, we'd like to have something like that. Uh-oh, too many bumps up here. So skewed on the high end, or positively, or to the right. Okay, there's some language for you. So you might like to take some notes on that if you've not seen that before. And let's go on and keep building up our language and our ideas here for describing what we're doing. We're doing descriptive statistics. We're describing what we've found in our data set. Okay, so let's go and have a look. Here we are. This is explicitly mentioned in the syllabus. Students should be able to use technology. So here's the Casio 9860 Plus graphics display calculator, a great little calculator there. And so what I want you to do is to turn the dude on and go to menu and drop down to stat mode. And if you select stat mode, you get this opening window. So what you need to do now is to where that highlight is now, if you start entering data, those 80 data points, and that's what I've done here, down to number 66 there. And if I hit execute now, I get this window here. Okay, so I've got my data set in list 1, and now what I want to do is to define my graph. So the first thing I'm going to do is to hit set, or choose set, by hitting F6, and then we get this window, and it's located on graph 1, and it's a scatter graph, list 1, list 2. So what do we want? We don't want a scatter graph here. We don't want a scatter graph. So if I now go to enter that, if I bring that highlight down so it's highlighted there, scatter graph, and how will I do that with these arrow keys just down below? I've left them out. Okay, we want to go down to there, and then it's a scatter graph. So what you want to do is, here are the options once you scroll down for that graph type. Our option's not there. We want a histogram, so go to the next window by hitting F6, and here are some more options. Come over here now. Here are some more options, and what do we want? Histogram. There it is there. So we'll hit F1, and it highlights histogram there. And it will also change these other entries, because with a histogram you need an X list and a frequency. Scatter graph you needed 2 different variables, X list and a Y list. Okay, so X list is list 1, so that is correct. Otherwise you have to scroll down there and change the list number. And the frequency is 1. Yes, we only had 1 of each of those data points entered. Okay, each one, it wasn't grouped already, we just put the 8 in. Okay, so what are we going to do then? We now have defined our graph, so if we hit execute and come back to this window, then we're going to set our or select our graph now of what we want to plot. So that's select, so go to F4, okay, hit F4, and you can see stat graph 1 draw on, so we've got to make sure that's on, and that's the only graph we want drawn at this stage. So if you now choose draw by hitting F6, you come up with this setting. Now this is very important. It's saying, look, your smallest value was 38, you want me to start there with a width of 3.34. What? How did they get 3.34? Well, that's a default setting on the calculator. It will always give you 10 groups, and starting at the minimum value. Okay, even if that value isn't convenient, like 38 is not a value you usually start a group interval at. Okay, and 3.34 is not the value you would have for the general width. So we want to change those there. So we'll just go down here and have a look. So here I've actually changed it to 35 as we did by hand, by scrolling down and highlighting and entering. So that was this button that's off the page here now. So that scroll down button just down there, and then scroll down to width and change that to 5 and hit execute. Okay, and then you get this, which is what we did by hand as well. Okay, so let's have a look. Theoretically that should be 35, that would then be 40. So we can actually read off along this scale for the widths of the group. If you remember back here of what you've set up, starts at 35, group width of 5. Okay, but there is something that you can do here, and that is if you hit F1 there, up comes a trace here, and if you do that, you get crosshairs that sit on the midpoint. Just watch this now. They sit on the midpoint of the graph, but specify the end point. So it sits in the middle and says this group starts at 35 with a frequency of 2. And if you scroll across again with this button here, then it will pop on the next group, and that will be 40. It sits in the midpoint, but it specifies the group starting point to the left of 40. Okay. Alright, so that could be then put on your piece of paper, so that you've asked the calculator to do all the hard work for you of grouping it. That could be then put on paper and hard copy with that scale, because you know what you're doing. You're starting at 35 and at a group interval of 5 and so on. And the frequencies will be given to you in each column. So it's all nice there for you. Okay, so that when that comes up, you just mark that on there, and then the next group and so on. But it has to have a continuous scale there. Alright, so what's the other thing that you can do? Well, if you hit execute there again, you'll come back to this window, and if you hit F1, you can get one var here. One var means it will calculate these statistics for you, using statistics in a way this time it's meaning values calculated. Okay, X bar is 55.4, so that's the mean. And then all these others we haven't looked at yet. Okay, but these are all values calculated on our sample, so that then becomes our set of statistics summarising that set of data. Okay, so you've always got those in the background there. If you don't just want a histogram, you want some calculations as well. Alright, so let's go on and see what we can do. Okay. The next thing that's quite handy is to work out where the set of data lies in terms of as you go through the groups. And this is called a cumulative, just cumulative or relative cumulative frequency distribution or frequency diagram. So what it does, it actually accumulates all the scores up to the end of a group. Now, it contains the total number of observations whose values are less than the upper limit for each interval. Why might you want to do this? Let's just stop and think. Alright, so you might want to know the number of students in our data living on less than 50 euros. Okay, living on less than 50 euros. That's what you might want to find. Okay, so that could be interesting, couldn't it? So let's set up a table which does that. So here's what we had before, living expense in euros, number of students. Now, cumulative number of students means we're going to accumulate all the students up to the end of a group. So there was 2 up to the end of the 40 group. There were 3 in the next group. So up to the end of that group, there's now 5. Get the idea? There was this 3 up to the end of the group plus the 2 that were in that previous group. Now, up to the end of 50... and this is the question I posed over here, there would have been all those 5 plus 11, there's 16 up to the end of the 50 group. Can you see what we're doing? We're actually accumulating the values, accumulating the frequencies. But actually, when we use the adjective, we use cumulative frequency, because accumulate is the verb and cumulative is the adjective. Okay, so 16, there's 21 in the next group, so up to the end of that group, there's 37. There's 19 in the next group, there's 37 plus 19, 56 up to the end of that group. 56 plus 11 in the next group, up to the end of that group is 67. 67 plus 13 is 80, because they're all contained up to the end of the last group. Instead of percentage of students as we had before, we could have cumulative percentage of students. So it's just this number divided by 80 times 100 again. Okay. So you could have percentages up to the end of that group. This can be very handy in asking questions about where students are lying within their groups. Okay, so a cumulative or relative cumulative frequency distributions are important. Relative means you're going to use a percentage here. It's relative to 100, if you like. It's a fraction out of the total, giving you some idea of the distribution. Okay, let's have a look at what it looks like. This is the cumulative line graph. Generally, we would do a cumulative frequency graph. These would not be straight lines generally in here. You'd smooth them out, okay? Because there's no proof or whatever that they jump straight through in a straight line from there to there. That you would actually have data points distributed in a curve through here, maybe. Okay. So we generally would not have a straight line. We would draw a curve like this. And as you must realise here, I guessed, mustn't, well, you never very judgmental must, but I guess you've realised that you can't ever go down. So if there's nothing in a group, let's just get rid of this. If there's nothing in a group, you might go flat, but you can't go down. Because you're adding up all those in the previous group plus the next group. So you can't go worse than flattening. If there's none in a group, and then it would go up again. So we generally use a smooth curve and then just taper it off. So here it is customary to taper this down just towards the 0 in the same interval width. So generally here, what have we got? I don't know here, cumulative frequency. So the first group is got 2 in it to the end of that group, and that's 40, so we'd start there, and we just taper that down to about half the group interval here, That's 5. So instead of there, halfway is here, and just taper it down, because that actually doesn't have any meaning back there. Only down to 35 is where it should be. All right, so how do we read it off again? Let's just get rid of all my scribblings here. You could say, how many students are living on less than 55 euros? Okay, so you could read that off there. Or about how many students are living, or living on, what could we do here? Let's say 63 euros, somewhere in here. Okay, we could read that back as well. So you can read some interesting things from this graph, and we're going to use it later on when we're going to be calculating other statistics as well. All right, so quite a useful graph. What's another thing? Let's do something else. I rather want to do something with this. What is the amount spent per week by 80% of students? 80% of students are spending less than 60, whatever this is, 63 or something, euros. So we could go that way. 80% of students are less than that. Okay, so all sorts of things. You've just got to be careful about what you're saying here with the interpretation, because it's less than, isn't it? It's all those up to a certain value. It used to be called a less than O guy sometimes, or you can draw a more than one, but we just draw a less than one now, accumulate them from the bottom to the end of the group. All right. Okay, got the idea? Let's go on and have a go. Here's your chance to show what you've learnt now. So here's a few questions, again from Pearson's, and what I want you to do is pause the presentation and then fast forward it, because the answers, as usual, are down below. Okay, so there's the first 3. We'll bring up 4 in a minute. Okay, 4, 5 and 6. Come down now. 7 only, 8's got a bit more coming up in a minute. Okay, here comes 8. Can we get on 9? I don't think so. Just 8 there. Nine. And let's have a go at 10. There's 10, and that's all we've got for you there. Some good ones. Let's have a look at some solutions. Okay, there's 1 A, B and C. And can we get D? Yep, D, E, most of F, I think. Yep, we'll just go up. We've got F, I think. F and G. Question 2, A to D. Question 3, and parts of 4 there. Let's come up 4. Yep, we've got all of 4 now. Here's 5. 5's got quite a bit of work happening there, so there's the first 2 graphs in 5. And the other graph in 5. Oh, we'll just come back here. Let's do it like this now. It's 6, part of 6. Rest of 6 there. Seven. Rest of 7. See if we can get some diagrams on there. Part B. And there's C. Let's look at number 8 now. A and B. We'll look at the last little bit in a minute. Okay, using the graph. Okay, let's look at 9. So let's look at part B now. And we're just coming up to number 10. Okay, and just the last little bit of 10 here. Okay, there we have it. Are you happy with that that presentation now, building up a bit of a skill level? Okay, so we're into it. We're away, we've got an idea of what we're about, and now we want to do some more calculations, a bit more graph drawing in the area of descriptive statistics. So for now, it's cheers from me. Catch you later.